Welcome to Module 2 lecture of Engineering Physics. This is all about kinematics. Another topic physics deals with is kinematics. Simply put in terms, kinematics is a branch of physics which studies the motion of objects. This would be coming from straight motion or curvilinear motion. As civil engineers, what is the importance of this topic in our profession? Because everybody loves to build things, we have to learn how those things move, so in case we are working for transportation and bridges, it would be good to know how cars move, how fast they go, what can be their top speed, how quick they can pick up speed, and also the braking distance. There are faster vehicles such as jets and airplanes involved with the study when constructing airports and runways, and yet there are rockets and space stations. What is rectilinear motion? As introduced earlier, this is the movement of a particle in a straight path. There are different concepts derived in rectilinear motion. Let's say that there is a straight path and we are to identify a reference point. If a particle from a certain starting point moves to the right, the particle would have an initial position moving to a final position. The distance between the reference point and the starting point of the particle is considered the initial position S0. Final displacement is considered from the reference point to the final position. Thus, displacement is taken as the difference between these two parameters, final and initial position. Similarly, the time when the particle started is considered as initial time or T0. The time when the particle reached its final position is considered as final time or TF. Delta time or time elapsed would be computed as the difference between the final and initial time. From prior analysis, speed or velocity is measured as the difference of position to that of time. As shown, it would be delta S all over delta T. And from calculus, you have learned that derivatives are changes. Thus, velocity is derivative of position to the derivative of time. Moving on to acceleration, this is measured as the change of velocity over time, which can be denoted as derivative of velocity to derivative of time. In terms of position, acceleration is taken as the second derivative of position to the second derivative of time. There are standard motion equations used for kinematics. As discussed earlier, the basic equations are that of velocity, which is equal to ds all over dt, and acceleration, which is dv all over dt. If we are going to extract time from both equations, we can get another basic equation, which is not a function of time. Let's do this by changing the equation of velocity into time. That would turn out to be dt is equal to ds all over v, and doing the same with acceleration, which would turn out as dt is equal to dv all over a. Then, if we place both equations as equivalent, ds all over v is equal to dv all over a. And by cross-multiplying, then the third basic equation is revealed. The fourth motion equation is velocity as a function of time. And we can derive this formula from the basic equation of acceleration, which is a is equal to dv all over dt. By cross-multiplying, the formula becomes dv is equal to a times dt. Then we integrate both sides, where the upper and lower limits for velocity would be final velocity vf and initial velocity v0, and final time t and initial time t0 for the other term. Take note that a in this equation is considered a constant. So, dv turns out to be v when integrated with its respective upper and lower limits, and the same thing with dt integrated as t with its corresponding limits. By expanding the limits, v would have vf less v0, and the other side will have acceleration a multiplied by t less 0. Thus, the formula becomes final velocity is equal to at plus v0 when taken to the other side to be positive. The fifth equation is solving for position as a function of velocity. Based from the basic equation of velocity, we convert it into ds is equal to v dt, where velocity have been derived earlier as the initial velocity plus at. Integrate both sides with their respective limits, taking note that the velocity and acceleration are considered constants. So, ds turns into s and v naught will have t, then at turned out as 1/2 at squared. Eliminating the limits will make the equation s less s naught is equal to v naught times t plus half of at squared. Placing s naught to the other side to make it positive gives us our equation. Another formula is solving for velocity as a function of position. Integrating the third basic equation, ADS is equal to V dV, the formula would turn out to be A times S is equal to half of V squared with their limits. Expanding it further gives us A times S less S naught is equal to half of V squared less V naught squared. And extracting v squared, we get v naught squared plus 2 times a times s less s naught. By checking the manner of our derivation, we initially have three basic equations whereby v is equal to ds all over dt yielded the formula for position. Acceleration dv all over dt gave us the formula for velocity in terms of time. And ADS is equal to V dV showed the velocity formula using position. Let's take an example. The velocity of a particle moving along a straight line is given by the formula V is equal to 3t squared plus 5t, where t is in seconds and v is in centimeters per second. If its position s is equal to 0 when t is equal to 0, determine its acceleration and position when t is equal to 6 seconds. The only given is the velocity expression, which is v is equal to 3t squared plus 5t, but it requires acceleration and position at a given time. So, in order to transform the given equation to the required, we are going to differentiate velocity to turn into acceleration. Thus, for acceleration at 6 seconds, we would have a is equal to dv all over dt, or that would be the differential of 3t squared plus 5t all over dt. And simplifying, we get an acceleration equation, which would be a is equal to 6t plus 5. If we plug in our t value, which is 6 seconds, that would come out as a is equal to 6 times 6 plus 5, which would turn out as 41 centimeters per second squared. For the next requirement of position, recall that velocity is just ds all over dt. So we can extract s by eliminating the differential symbol, or that would be integrating the whole equation. So we integrate ds is equal to the integrate of 3t squared plus 5t dt. If we are going to have it simplified, s is equal to t cubed plus 5/2 of t squared. And plug in the value of t, which is 6 seconds, to have the position of 306 centimeters. Free falling motion considers a straight vertical path. The basic motion equations would remain the same, and the other derived equations are just modified, with position such as s is equal to s naught plus v naught t plus half of at squared, for y is equal to y naught plus v naught t plus half of gt squared. Velocity, which is equal to v naught plus at, would turn out to be velocity is equal to v naught plus gt, and velocity squared is equal to v naught squared plus 2a times s less s naught would be equal to velocity squared is equal to v naught squared plus 2a, this time y less y naught. Take note of the difference between speed and velocity and distance and displacement. Speed and distance are scalar and they will always be given as positive. For velocity and displacement, we take those going to the right as positive, while those going to the left as negative. And similarly, going upwards are positive, and those which are falling are said to be negative. Let's take this example. Coyote drops from a cliff. Determine the following. A. His speed after 6 seconds. B. His velocity at that time. C. The distance he traveled during that time. And what is his displacement? Since Coyote dropped, our initial velocity will be taken as 0, with that given t as 6 seconds. Speed and velocity can be solved using the equation final velocity is equal to v naught plus a times t. Plug in initial velocity as 0. Acceleration due to gravity will always be negative 9.8 meters per square second, and the given time of 6 seconds, giving us the answer negative 58.8 meters per second. With the answer, we take the speed as positive 58.8 meters per second, while velocity as negative 58.8 meters per second, showing that Coyote was moving downwards. Solving for the distance and displacement would entail that we use the formula S is equal to V naught t plus half of AT squared, whereby V naught times t will become 0 due to 0 initial velocity. So plugging in our given, we would have S is equal to half of negative 9.8 meters per square seconds times 6 seconds squared, which will give us our answer negative 176.4 meters. Again, distance is a scalar quantity, taking positive 176.4 meters, and displacement is going to be negative 176.4 meters, showing downward motion. Hang on tight for the next module about dynamics.